Hi, my name is Yuxin. The topic of my FYP project is Advanced Image Understanding with Deep Learning in Real-World Applications. My project will be focused on data augmentation and segmentation for 3D brain MRI images. Image segmentation and augmentation are crucial to biomedical imaging applications. Many CNN methods rely on supervised learning with large labeled dataset. However, we are facing the challenge of limited labeled data. Obtaining medical images is difficult due to privacy issues, and labeling medical images requires significant expertise and time. Hence, data augmentation and segmentation are used to overcome this challenge. These are the reference research work related to my project. The baseline model is mentioned in the first paper. This figure shows how the baseline model brainstorm model works. Brainstorm model requires only one label scan and leverages other label scans in an unsupervised approach. One label images and other unlabeled images are passed through spatial model and appearance model to learn the respective transformations. Spatial transformation is a spatial deformation field, and appearance transformation represents the intensity change. By using these transformations, it aligns the fixed label image to unlabeled images and hence synthesize images and labels. However, the current methods still have some limitations. Firstly, there is still room for improving segmentation performance. Secondly, the number of brain examples with distinct anatomical structures are restricted by the number of spatial transformation learned. So our objective is to eliminate the limitation of current method. We want to improve the segmentation performance of current model, and we want to use current model to generate more images with distinct anatomical structures. For improving segmentation performance, we have done 3 experiments. Firstly, we fine-tune the settings of the loss functions of the spatial model. Secondly, we implement a Siamese model to get the similarity score between 3D brain MRI images. By doing that, we select the brain MRI which are more similar to the fixed label atlas. Thirdly, we implement a classification model to filter out the brain images with irregular shapes. Other than that, we also did an experiment to synthesize more reliable brain examples by sampling a continuous set of spatial transformation. For our project, we use IXI dataset for healthy brain images, and we use Atlas dataset for lesioned brain images. FreeServer is used for data preprocessing, and it performs tasks like skull strip and volumetric labelings. Batch generators is used for data augmentation. It generates the images which are similar to fixed reference volume for Siamese network, and it generates the images with irregular shapes for classification model. In this work, spatial model is a more determining factor of segmentation performance. Because the anatomical differences between images are learned by spatial model, and the synthesized labels are generated by only applying spatial transformation. Loss function is also a crucial step in the current model, as it provides feedback during model evaluation, contributing to model weight update and model optimization. Hence, in our first experiment, we narrowed down our research scope and focused on investigating the loss functions of the spatial model. The parameter alpha and lambda are added to similarity loss function and smooth loss function. We wanted to perform the sensitivity analysis on 2 terms of loss function. A greedy search was performed. By studying the 2 loss functions, we aimed to improve the segmentation performance, generating more accurate segmentation labels. Brainstorm model captures the distribution of the anatomical appearance differences between images. The labeled reference value X is aligned to a target unlabeled image by using deformation model. The brainstorm model returns a dense displacement vector field depicting the displacements between voxels of brain MRI image pair. However, if the displacements are too big, the brainstorm model may not perform well. Hence, we use Siamese network to select the unlabeled images that are relatively more similar to labeled reference value X. In Siamese network, it has a hypothesis that if the 2 image inputs belong to the same class, their feature vectors are very similar, while if the 2 images are from different classes, their feature vectors are very different. Hence, the element-wise absolute difference between the two feature vectors from the same class and different classes must be different. So, as we can see in our architecture, both images are passed through the CompNet and obtaining the feature vectors. Then we calculate the absolute difference between two feature vectors, followed by a fully connect layer. Finally, we get a similarity score. After free server preprocessing, a portion of training images generated are with irregular shapes. From observation, we discovered that the segmentation performance of brain images with irregular shapes are lower than the average segmentation performance. Hence, we use a simple classification model to quickly filter out the brain images with irregular shapes, thus improving the segmentation performance. This is a model architecture of the classification model. The CompNet are also used in Siamese network. So the input passed through a CompNet layers and followed by two fully connect layers. Brainstorm model samples transformation from a discrete set of appearance and spatial transformations. With 1 fixed images and 100 unlabeled images, we can learn 100 spatial transformations, synthesis 100 labeled examples with distinct anatomical structures. The number of synthesis examples can be further extended if we convert the spatial transformation into a continuous set. By taking an intermediate state in spatial transformation and applying it to the fixed reference image X, infinite new images can be synthesized. This can be used as a data augmentation method to generate more brain images for medical application. From our observation, in Brainstorm model, sampled spatial transformation is achieved by extracting an FI matrix. FI matrix represents spatial deformation flow. So in our experiment, we adjust the FI matrix by setting it as 0.5 f to synthesize the new images. Here is the overall result for segmentation performance. As we can see, all three methods outperform the baseline method in mean die-score across all the validation data images. Now, we will go into details to talk about the results. Here is the result of grid search on the parameters alpha and lambda. In the baseline model, the weights of these two loss functions are set to be 1 to 1. Our experiment result shows that for alpha, the die-score is the highest when alpha equals to 0.8 and lambda equals to 1. For lambda, the die-score is the highest when alpha equals to 1 and lambda equals to 1.5. The experimental result shows that the model is more sensitive to alpha and the model is more robust to lambda. Alpha is a more determining factor to achieve a higher die-score. Adjusting lambda is a safer choice to improve the segmentation, while extra attention should be paid when adjusting alpha. For the second experiment, we train the Siamese network and predict similarity score across 120 atlas images. Then, we select the 40 images with higher similarity score and 40 images with lower similarity score to perform the segmentation training. As we can see from the result, the die-score of higher similarity score dataset is higher than the lower similarity score dataset. The image below shows that when aligning the label of fixed images to unlabeled images, the images with higher similarity score performs better. For the third experiment, we train the classification model and make prediction across 120 atlas images. We filter out the 40 images with higher irregular shape score as group A and randomly select 40 images among the rest of the images as group B. As we can see from the result, the die-score of group B is much higher than group A and also outperforms the die-score of original data. For the fourth experiment, we adjust sample transformation, which is an FI matrix, to a continuous set. This figure shows the difference between synthesis images by applying matrix F and 0.5 f. The sampled spatial transformation in B is more smooth than that in A, and the transformed images in A is more similar to sampled unlabeled Y in anatomical structure. This shows that it is possible to synthesize more images and labels by using a continuous set of transformation. The experimental result shows that loss functions in spatial model improve segmentation performance significantly. Similarity loss function is a more determining factor for higher dice score, while adjusting smooth loss function is a safer choice for segmentation improvement. The experimental result shows that if unlabeled images is too abnormal or too different from the fixed atlas, it negatively affects the segmentation performance. So, filtering out abnormal and very different images can improve the segmentation performance. Another benefit of performing image filtering in early stage is it will not increase model complexity and training time. Moreover, after image filtering, fewer datasets will be evaluated, and this will decrease the training time. Our experiment also shows that applying continuous set of spatial transformation by adjusting the affine matrix can generate more distinct new examples. We also learn the limitation of brainstorm model from our experiment. Firstly, its low tolerance towards abnormal images. When we use abnormal images in model training, it might synthesize images that are out of shape. Secondly, its incapability of capturing the spatial relationship between different parts of brains. Brainstorm model learns the anatomical differences between corresponding voxels of two brains and their neighboring voxels. However, it is unable to learn relationship if two voxels are far apart. For lesion brain, the size and location of lesion parts in different brains might be very different, so brainstorm model fails to perform segmentation for lesion brain images. Several experiments can be performed in the future. Firstly, we can use intermediate image synthesis for a continuous set of spatial transformation for brainstorm model and Siamese network. Secondly, Siamese network and classification model are feasible to apply on other anatomy or image modalities. Thirdly, currently we either train the model fully on healthy brain dataset or fully on lesioned brain dataset. However, in the future, we can mix lesioned brain images and healthy brain images to generate intermediate examples for training. This is the end of my presentation. Thank you.